Today we will learn about rotational of rigid body. In this chapter, you will define this parameter. For equilibrium of rigid body, you will define this. In rotational dynamics, you will expose to this. And for the last subtopic, which is conservation of angular momentum. The linear motion, as example, this moving car. When the car starts moving from one point to another point, it will have a displacement. So we define the displacement as the distance between initial point and final point in a straight line. In rotational motion, when the object rotates from one point to another point, it also has displacement, but we represent it as theta, which is called angular displacement, theta. So, we define the angular displacement theta as an angle through which a point or line has been rotated in a specified direction about a specified axis. Now, let's go to the next parameter used in rotational motion. We still refer at the same example. The moving car also will experience a velocity when changing its displacement. In linear motion, we define velocity v as the rate change of displacement. While the car is moving, the tire of the car is rotating. So the tire also experiences velocity, but in rotational motion. We can define average angular velocity denoted as omega as the rate change of angular displacement, or omega is equal to the rate change of theta divided by time interval. At the instant time, instantaneous angular velocity can be defined as the instantaneous rate of change of angular displacement, omega equal to d theta divided by dt. When the angular velocity of a rigid body changes, it has an angular acceleration denoted as alpha. Average angular acceleration in time interval can be defined as the rate change of angular velocity, or alpha equal to change of omega divided by time interval, while the instantaneous angular acceleration is defined as the instantaneous rate change of angular velocity.
An acrobat standing on parallel bars. Two children on a seesaw. A beam which is being raised by a crane. And a ladder resting on a wall. All these objects are in a state of static equilibrium.
Generally, actually torque is turning effect of force.
In physics, the movement of a revolving door is the rotational motion of a rigid body. This rotation is caused by a force applied to the body in a particular way. The effect of the rotating body depends on three parameters: the magnitude of the force, the distance between the point of application of the force and the axis of rotation, the angle made by the force with the vector r, connecting the axis of rotation with the point where the force is applied.
The magnitude of the torque is defined as the product of a force and its perpendicular distance from the line of actions of the force to the point, rotational axis. Or we can define as torque equal to F cross R, which is F R sine theta, and the theta is the angle between F and R. In the chapter of linear motion, the tendency of a body to keep moving when it is set in motion results from a property called inertia. First of all, this moment of inertia is really just the rotational inertia. In other words, how much something going to resist being angularly accelerated. For comparison, a boy kicked the ball and the rolling bowling ball toward the pins. For the ball to roll after has been kicked, it should be very easy, relatively easy to get the ball angularly accelerated. Compared to the bowling ball, it has large moment of inertia. Because of its mass, it's going difficult to bowling ball to angularly accelerate. Now look at the moment of inertia of a system which contains a few masses. The system consists of particles M1, M2 and M3. Rotates anti-clockwise from its rotational axis R1, R2 and R3. To calculate moment of inertia I of the system, we should sum all of I for all particles. So, we can define the moment of inertia of this system as the sum of the products of the mass of each particle and the square of its respective distance from the rotation axis. We also can write the formula as summations of m r squared. We are now ready to develop the fundamental relation for the rotational dynamics of rigid body. Look at the man push the trolley. He pushed the trolley. He just gave a force to the trolley and caused the trolley to accelerate forward. So we can express the relation between force and acceleration as F equal to ma. Now look at Mr. Crab. He pulling the money from the well. He exerts the force perpendicular to the distance of the pulley, caused the pulley to rotate with angular acceleration. Before this, we have defined torque as the product of the force and its perpendicular distance. In this example, relationship between torque and angular acceleration can be write as torque equal to I alpha. To memorize this formula, you can just do this thing. F is analogous to torque, m is analogous to I, and A is analogous to alpha. When F is equal to ma, so that torque equal to I alpha. In rotational motion, we represent momentum as angular momentum. L. Angular momentum is just how much momentum object have in rotational motion. Every rotational quantity that we have encountered is the analog of some quantity in the linear motions of particles. The analog of linear momentum P is called angular momentum L. The analog of mass m is called moment of inertia, represented as I. The analog of velocity v is called angular velocity, represented as omega. When p is equal to mv, we can define angular momentum as L equal to I omega, or angular momentum is the product of angular velocity of a body and its moment of inertia about the rotational axis. Now, let us see practically how angular momentum L, moment of inertia I, and angular velocity omega are related each other.
Skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Good morning. Let's learn about conservation of angular momentum. But before we do, let's review the equation for conservation of linear momentum. Bo, what is that equation?
Flippin' physics! The sum of the initial linear momentum of a system equals the sum of the final linear momentum of a system.
And remember,
linear momentum is a vector.
Thanks, Bo. Bobby, what then do you think is the equation for conservation of angular momentum?
The sum of the initial angular momentum of a system equals the sum of the final angular momentum of a system.
But remember,
angular momentum is a vector.
As a conclusion, conservation of angular momentum states that a total angular momentum of a closed system about an rotation axis is constant, or we can just write summations of initial angular momentum is equal to summations of final angular momentum.